All right, so welcome to lecture 9 of 124105. This lecture actually wraps up the topic on direct current circuits, right? This is also the third week of the course. And so throughout the first 3 weeks and the first lectures prior to this, we developed the topic in which we eventually arrived at the definition of current and voltage, and then we started to analyze circuits. So in this lecture today, we will wrap up direct current circuits by combining two of the circuit elements that we have learned in the first 8 lectures. So we learned about the resistor. Resistor in a circuit, it controls the flow of the current by having a resistance across its terminals. And then we also learned about the capacitor. It's the circuit device that stores charge and therefore stores energy in the circuit. So in today's lecture, we will combine the resistor and the capacitor in a circuit, and hence we have what we call the RC circuit. RC, of course, stands for resistor capacitor circuit. And then we will analyze the circuit in terms of storing energy in the capacitor and also accessing the energy stored in the capacitor. So we will just a brief review of what we've learned already. When we learned about the capacitor, we saw this illustration. It consists of, two conducting plates, and those plates carry opposite signs of charges. One plate is positively charged, the other plate is negatively charged. And we learned that the capacitor stores charge. If you connect the capacitor plates across a battery or a voltage source, then positive charges start to accumulate on the plate connected to the positive terminal, and negative charges start to accumulate on the plate connected to the negative terminal. And we saw this equation, which gives us how much charge is stored in the capacitor plates. C is the capacitance, tells us the property of the capacitor to store charge, and V is the voltage across the capacitor plate. So we learned that as the capacitor charges up, voltage starts to be measured across the plates of the capacitor. And we learned that it's this ghost room again from semester 1, right? So let's try to see what's going on here. Guys. Just pause this. Right, so and the key thing about the capacitor, right? If you connect it to the battery, it starts to charge up. And we said that the capacitor is fully charged if the voltage between the plates is equal to the battery voltage, okay? And therefore the maximum voltage you can have across the plates will be equal to the voltage of the battery or the source. So we learned this when we encountered the capacitor, but we did not really discuss what actually happens during the charging up process, right? You connect the capacitors to the plates, the capacitor charges up. That's all we've learned. But what exactly happens during the charging process is what we will learn today, right? So of course, to charge up the capacitor, you'll need to connect the capacitor to a battery. So here is the circuit diagram for the charging of a capacitor. The key distinguishing feature, right, is the presence of the battery or the voltage source, yeah, because then the voltage source charges up the capacitor. You have wires connecting the capacitor to the battery. So you have some resistance. So this resistance R can come from an independent resistor that you put in your circuit, or it could also come from the intrinsic resistance in the wires that you use to connect your capacitor to the battery. So there will always be some resistance in the circuit. And hence you have an RC circuit, a resistor and a capacitor circuit. But during the charging up process, again, one way to distinguish whether the circuit is for charging the capacitor is to check whether there is a battery present in the circuit. Right, so here's your RC circuit. Initially, the capacitor is uncharged, so Q is equal to 0. If you close this switch so that you create a closed circuit, current can therefore flow. And we said that current flows from the positive terminal to the negative terminal of the battery. Hence, you have this direction for the current flow in the circuit. The charge starts to accumulate on the capacitor plates. And if we analyze this circuit, we'll see that the resistor is in series with the capacitor, right? They're in series connection. And we've been learning that if resistors are connected in series, the voltages add up. That concept also applies to whether you're connecting a capacitor and a resistor together. So since the resistor is in series with the capacitor, the voltage across the resistor should also add up with the voltage across the capacitor. The voltage across the resistor and capacitor should equal the voltage of the battery. Okay, so you have this sort of Kirchhoff's loop rule equation, which satisfies conservation of energy. Okay, to understand what's happening during the charging up process, let's expand this equation using the definitions for Ohm's law that gives us the voltage across the resistor, V is equal to IR. And let's use the definition of the capacitor that relates the charge stored to the capacitance and the voltage across the capacitor. So you have the voltage across the capacitor is equal to the charge divided by the capacitance. So if we substitute those definitions into this conservation of energy or this voltage equation here, you have IR plus Q over C is equal to the battery voltage. Okay, written in this form, it actually tells us many important things. So notice this is an equal sign. So that means right-hand side is equal to the left-hand side, which essentially means that as the capacitor charges up, right? As the capacitor charges up, the charge across the plate increases. Hence, the second term, Q over C, increases, right? Q starts to build up, Q increases. And in order to conserve this relationship, right, if Q increases, therefore the current, which is the first term here, needs to decrease, right, in order for to keep the value of the voltage across the battery constant. So we're assuming that the battery is an ideal voltage source. It has no internal resistance. So it has, like, for example, 9 volts across its positive and negative terminals. So if we were to keep the 9 volts voltage of the battery constant, if the charge in the capacitor plates increases, then the current through the resistor should decrease, right? And that then conserves the energy and satisfies Kirchhoff's loop rule or voltage rule, such that after a very, very long time, as time approaches infinity and the capacitor is fully charged, you will have then a maximum Q across your capacitor plates, right? You have a maximum Q there, and therefore the voltage will be maximum. It will be equal to the battery voltage, because we said the capacitor is fully charged if the voltage across its plates is equal to the battery voltage. Hence, if the voltage across the capacitor plates is equal to the battery voltage, what should be the value for the current? The current should be 0. So the current should approach 0 as the capacitor becomes fully charged, right? Does that make sense? It's sort of what's happening during the charging up process. And maybe it's easier to visualize what's happening. So here is how it looks like, right? You have here the Kirchhoff's loop rule equation that relates the voltage across the battery is equal to the sum of the voltages. Right? At time t is equal to 0 when the capacitor is uncharged, that's that point here. Right? Time t equals 0, the capacitor voltage and the capacitor charge, they're both 0. Okay? But the current in your circuit is maximum. Yeah, this is time t equals 0 at this point. Right. And how do you calculate the maximum current in your circuit? You calculate it using Ohm's law. So the maximum current will be the voltage across the battery divided by the resistance of the resistor. Okay. So you start with a maximum current and a 0 charge and 0 voltage across the capacitor. Now, as the capacitor charges up, notice how as time increases, the voltage, right, and the charge in the capacitor increases, right? And as the charge and the voltage across the capacitor increases, notice how the current decreases at the same time. All right. That therefore satisfies this relationship here. And as time approaches infinity, right, at the very, very long time, after a very, very long time, the charge stored in your capacitor plates approaches the maximum charge that can be stored. And therefore, the voltage across the capacitor plates approaches the voltage of the battery. And notice what happens to the current. The current approaches 0 after a very, very long time. Right? Good, does that make sense? I hope easy enough to understand and sort of remember. Now the x-axis is time. Let me define a special time, right? And I'll call this special time tau, the Greek symbol tau, right? I'll define this special time tau as the time it takes for the voltage and the charge to reach 63% of the maximum value. Right? So when the charge stored on the capacitor plates is 63% of the maximum possible charge that can be stored, or if the voltage across the capacitor plates is 63% of the battery voltage, then that's the time tau. Okay. There's a corresponding current for that particular time, right? It's also tau. For the same time when the charge stored is 63% of the maximum value, the current in the circuit is would have gone down to 37% of the maximum value. Okay, and we will talk more about this special time tau in the next few slides. But before we talk about tau, tau is in fact called the time constant, and we'll talk more about that. But this slide summarizes the equations, the relevant equations that are important in determining the charge stored across the capacitor plates, the voltage across the capacitor plates, and the current in the circuit during the charging up process of the capacitor. So in this equation here, T is time, any arbitrary time for when you want to determine the charge, the voltage, and the current, right? So that's the small t there. Tau, of course, you have there tau. It's the same tau here. It's called the time constant. It's the value of the resistance times the value of the capacitance. Okay. You will see in this equation here, E. Okay, E, I know we use E for the electron charge, the elementary charge for an electron, but it's E here represents the constant 2.718, blah, 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 which you can access that as the E exponent X in your calculator, which is what you'll use to solve for these equations here. Right, so I would say these equations are important. If you're building a formula sheet for the test, these are fundamental equations that I would recommend you put in your formula sheet. Right, they're all exponential. So the E here tells you that the change in the charge, voltage, and current, they're all exponential. And that's why the graph looks as like this, right? There's an exponential increase in the voltage and the charge, and an exponential decrease in the current during the charging process. Right. Now on to the time constant tau. Okay, the time constant tau, we define that as 63% and 37%. Let's see why it's 63% and 37%. So let's look at the charge and the voltage equations, right? This is the equation for the voltage and the charge. Now, if we sort of try and figure out how much charge is stored when the time passed is equal to the time constant tau. Hence, we substitute time t here to be equal to tau. We have, therefore, this thing becomes -1. And E is just a constant number. So we can actually solve this whole thing that's just a constant number. E exponent -1, that's equivalent to 1 divided by E. Okay, and if you do 1 minus 1 divided by E, you have 1 minus this 0.36788, right, which gives you 0.63. Hence, at time t is equal to the time constant tau, the voltage across the capacitor plates is equal to 0.63 of the voltage across the battery. Okay? And that's why tau, the time constant t here, is the time it takes for the voltage across the capacitor to charge up to 0.63 or 63% of the battery voltage. Make sense? All right. We can do the same exercise for the current, for the charge. I mean, the equation has the same form. And so similarly, you end up with 0.63 of Q max. Okay. So at time t equals time constant, you would have stored 63% of the maximum charge that the capacitor can store. Right, and hence that's why it's 63%, which was defined in the graph. Right. Okay, if we do the same exercise for the current, okay, here's the current equation. This is how the current decreases over time as you charge up your capacitor. If you try to determine what's the current in your circuit at time t is equal to the time constant tau, and you substitute t here with tau, and therefore you have tau divided by tau, that's just equal to 1. Hence you have e to the -1, or 1 over e. 1 over e is 0.36788. Hence, at time t equals tau, the current in your circuit is 0.37 coming from here, 0.37 or 37% of the maximum currents originally flowing in your circuit. Right. Hence, we define tau, the time constant, as the time taken for the current to decrease to 37% of its maximum value. Good. So that's the formal definition of the time constants, right? Those percentages, 63% for voltage and and charge, 37% decrease for the current, and you calculate the time constant tau just by from the resistance of the resistor and the capacitance of the capacitor. So you can easily determine time tau given the circuit and the resistor and capacitor values. But these are all numbers. Practically, what does the time constant mean? Practically, the time constant determines the charging rates of your capacitor, right? And it tells you that how fast your capacitor charges depends only on the product of the resistance and the capacitance. Right. So more importantly, the physical significance of the time constant tells you how fast your capacitor charges up. And the fact that the time constant only depends on the resistance and the capacitance, that means that if you build an RC circuit for your timing electronics, for example, all you need to do is adjust the resistor and the capacitor values in order to achieve the charging rate that you need in your circuit. Right? How fast it gives you how fast the capacitor charges up, meaning if you have a large time constant, right? Remember, tau, time constant, is all about time. So if you have a large time constant, that means you have a large time. Large time means slow, right? Right? If you're moving slowly, it takes you a long time. So a large time constant means a slow charging up of your capacitor, of your, and therefore your RC circuit. And of course, therefore, a small time constant means that you're charging up your capacitor faster. Right, does that make sense so far, the concept of charging a capacitor? I hope it's relatively straightforward. Good. Any questions? No. All right, so as the capacitor charges up and charge builds in the capacitor plates, we also learned before the capacitor essentially stores energy. It's an energy storage device. We already encountered this equation here, right? The energy stored across the capacitor plates is 1/2 CV squared. V will be the voltage across the capacitor plate. So if if you want, for example, to determine how much energy is stored 2 milliseconds after the capacitor starts to charge up, before it's fully charged, then you have the tools, you have the equation, you have to use this voltage equation, right, to determine how much voltage is across your capacitor plates, and from there determine the energy stored across your capacitor plates. Yeah. We'll look at an example of this later on, right? But any questions about the charging up process? No? Okay, so let's now go to the other process, the discharging process, right? So first we started with an uncharged capacitor, connected it to a battery or a voltage source. The capacitor charges up, energy is stored across the capacitor plates, right? We then start with this fully charged capacitor. Okay, if the capacitor is fully charged, the voltage across its plates is maximum, and so is the charge. The charge stored in its plates is maximum. The energy stored is also maximum. And because the capacitor stored energy, it can act like a voltage source, like an energy source. If you look at this capacitor, right, one plate is positively charged, the other plate is negatively charged. It sort of looks like a battery, looks like a voltage source. So in fact, your fully charged capacitor can act like the voltage source or the battery. So that if you connect your capacitor to a resistor or to an external load, or you connect your fully charged capacitor to a circuit that you want to power up, right? And you complete the circuit, closing that switch, your capacitor then acts like the voltage source, and energy flows in your circuits, right? Currents, in other words, current will flow. Again, the current flows from the high potential point, positive plate of the capacitor, to the negative plate of the capacitor. So you can see here, your fully charged capacitor sort of acts like the voltage source, right? Okay, right, there's a resistor in your circuits. Again, the resistor can come from a resistor that you intentionally put in your circuit, or it could be the resistance of the wires that you use to connect your capacitor plates, or you connect to your circuit. And because there is a resistor dissipates energy, right? Resistor is like the electrical friction that dissipates energy. And because there is a resistor, the resistor dissipates energy. It causes the current to decrease exponentially, and therefore it causes the voltage, right, across the capacitor plates to decrease as well. And as the capacitor discharges, the charge across its plates decreases. So there's an exponential decrease in all the quantities involved. So in the charge, voltage, and the currents. Notice how the equations all have the same form, right? There's an exponential decrease in the charge, right? As sort of makes sense, because your capacitor discharges, the charge across its plates decreases. As a consequence of charge decreasing, the voltage therefore decreases. And if the voltage decreases, then the current through your circuit also decreases, such that as time approaches infinity, after a very, very long time, and your capacitor becomes fully discharged, then of course, there's no more charge across the plates, there's no more voltage, and there's no more current, and all of them therefore approach zero. Good, sort of makes sense, right? I hope, right? And because the equations all have the same form, you can expect that if we make a graph of and visualize how the charge, voltage, and the current decreases over time, you have again this E, this exponential decrease in the charge, voltage, and the current. So you have this exponential decrease here. Initially, at time t is equal to 0, the voltage, that's the maximum voltage, charge, and current. You can calculate the maximum current from the maximum voltage of the capacitor divided by the resistance in the circuit. So you start with maximum values, and as time approaches infinity, you approach 0 values for the charge, voltage, and current. And once again, we can define this special time tau, which is the time constant. It's 37%. It's the time it takes for the voltage, charge, and current to decrease to 37% of the maximum original value. And if we talk about the time constant for the discharging process, it's the same concept. It's still resistance times the capacitance. But this time we're talking about the time it takes for the voltage, the charge, and the capacitance and the current to decrease to 37% of its maximum value. Practically speaking, again, the discharging rate or how fast your capacitor discharges depends only on the resistance and the capacitance value, right? And therefore the time constant gives you how fast the capacitor discharges. Once again, if you build a capacitor to sort of in your circuit to control some electronics, right, all you have to do is to adjust the resistance and the capacitance values that you will use in your circuit to determine how fast your capacitor discharges. Okay. Again, a large time constant means big time. The process is therefore slow. And a small time constant means that it takes a short amount of time to discharge the capacitor, and therefore that tells you a fast discharging rate. Right. Any questions about the discharging process or the charging process? If any question comes up to mind. So if you have an RC circuit, the capacitor can charge up and it can also discharge, right? It charges up if you connect the capacitor to a battery, and then if you disconnect the capacitor from the battery, it discharges, and you can repeat this process of charging and discharging of the capacitor. So the RC circuit is actually quite important. So you have here, this charging, discharging, charging, discharging process. And in fact, any electronics that operates intermittently, like for example, strobe lights and blinkers, they have an RC circuit in them. The blinking of the lights is controlled by an RC circuit, right? So you have there the charging up of the capacitor. And then when the capacitor discharges, it emits this large energy, and that therefore creates, you sort of have this maximum current in your circuit that probably triggers the lights to shine. And then your capacitor discharges, it charges up again. Again, when it discharges, again, it releases this burst of light because you have current in your circuit, and the process repeats. Likewise, windscreen wipers, it operates intermittently. It has an RC circuit. And by controlling, for example, the charge, how fast your capacitor charges and discharges, you can control, the frequency of your windscreen wipers or the frequency of the blinking of the lights. So RC circuits are quite important, and it depends on the charging up and discharging of the capacitor. Right, any questions about the RC circuit, the process behind charging and discharging? Right, no questions, right? If there are no questions, then we're now left to just practice how to apply those equations and how to solve problems involving charging and discharging of a capacitor. So here's a particular circuit, RC circuit. Okay, you have the capacitor 20 microfarads, right? Micro, again, times 10 to the minus 6. And you have a resistor 10 kilo ohms, kilo times 10 to the 3. Okay, by looking at the circuit that's given, can you tell whether it's a charging or a discharging kind of RC circuit? But without looking at the title that I put there. Seeing that there's a 6-volt battery, or seeing that there's a voltage source, should give you the clue that it's an RC circuit for charging up the capacitor, right? Okay, so if you see a battery there, then right? It's a charging up process, right? So if you have equations here, which equations should you use to solve all the questions here? Right, the charging up process will be these equations here. These are the charging equations, right? And these ones are the discharging equations, because in the discharging equations, the equations take on similar forms, right? The charge, voltage, and current, they have similar equations. For the charging up process, you have these equations here, because the charge and the voltage increases during the charging up process, but the current decreases during the charging up process. So because different things are happening to the charge and the current, you have different equations, forms of equation. The form of the equation is different for charge and current. Okay, right. So that's perhaps 50% of answering the question right there. Okay, so let's proceed to the questions themselves. Calculate the time constant for the circuits. This is quite a favorite question because it's crucial. So time constants, you only need the resistance value and the capacitance value, right? Don't forget to include your prefixes. So that's 10 times 10 to the 3 times 20 times 10 to the minus 6, 0.2 seconds, or sometimes it's easier to work in milliseconds. So I'll convert that 0.2 seconds to 200 milliseconds. I should have written my solutions here, but I'll just carry that over. Right. You will see in the next question why I've chosen to convert my time constant to milliseconds. So in the next question, it asks to calculate the current in the resistor at 50 milliseconds, meaning 50 milliseconds after the switch was closed or 50 milliseconds after the capacitor started to charge. Okay, we already determined that the charging equations are these equations, and we want to find the current. So the current is given by this equation here, I max e to the minus t over tau, right? I need to find I max. I max is the maximum current in the circuit. And you can find that by taking the battery voltage, dividing that by the resistance, right, using Ohm's law. So you have 6 volts divided by 10 times 10 to the 3 ohms. Gives you a maximum current of 0.6 times 10 to the minus 3 amps, or 0.6 milliamps. So you'll need that for your Imax here, 0.6. Right. I include the units here so that we're all aware I'm working with milliamps rather than amps. E to the minus t, small t, is the time where you want to determine the current. So here the question says you want to determine the current at time equals 50 milliseconds. Right, so that's 50 milliseconds divided by tau, which is the time constant, and hence why I chose to convert my tau to milliseconds. It's for consistency of units. Right, so then I don't have to convert my 50 milliseconds to seconds if I work with tau in milliseconds, because then the units just cancel out in the equation anyway. Right, so just be conscious with units. Right, it's fine to work with milliseconds or seconds, just be consistent, right? Because then if you're not, you will lose some decimal places. Assuming you've entered this E correctly to your in your calculator, right? Use the e to the x function in your calculator where x is equal to -5/200, right? You should get 0.467. And we are working with milliamps there. So the unit is milliamps. There's some dinosaur somewhere there. Good. Any questions with the solution? Yeah. Okay, next we want to calculate the voltage. So the voltage equation is here. So hopefully, yeah, right, it's a direct substitution. We need the voltage of the battery, that's 6 volts times 1 minus e to the negative time t. Again, t is given in the question. You want to find the voltage at t equals 100 milliseconds. So I leave the units in 100 in milliseconds because I will use my tau in milliseconds, right? So e to the negative t divided by tau. Tau is 200 milliseconds, right? And again, so milliseconds will cancel out there. So it's okay to leave your current values in milliseconds. And again, assuming that you entered the E correctly in your calculator, right? If maybe use some brackets, it's 1 minus E to the yeah, so 1 minus this whole thing. If your calculator is fuzzy with brackets, it's 1 minus this whole E to the negative 100/200. You should get a voltage of 2.361 volts for this case. Right, next question, electrical potential energy stored in the capacitor. That's E is equal to 1/2 CV squared, where V is the voltage across your capacitor plates at this particular time when you want to find the energy at. Okay. Right, so this VC here in the energy equation, this is not 6 volts. VC is not 6 volts. It's only 6 volts if your capacitor is fully charged. But at time t equals 1 second, perhaps your capacitor is not yet fully charged. Hence, you have to calculate first, find VC at t is equal to 1 second, or 1 second is 1,000 milliseconds. Okay. Right, so do this exercise to find VC, okay, as you did in question C to find VC, except that the time you'll use is not 100 milliseconds, but rather 1,000 milliseconds or 1 second. If you do that, you should get a VC is equal to 5.96 volts. So you can see that it's not yet quite fully charged. Well, depending on rounding, you can argue it's fully charged. But the point is, if you want to calculate the energy at some given time t, unless you are sure that the capacitor is fully charged, in which case you can use the voltage of the battery to calculate for the energy stored. Unless you're sure about that, then you have to calculate the voltage across the capacitor plates using this equation here. Okay, and then use that voltage to calculate for the energy. So that's 1/2 times the capacitance 20 times 10 to the minus 6 times the voltage across the capacitor plates 5.96 should give you an energy equal to this. Good. All right. Okay, and the last question needs a little bit more math. Okay. So let's go to the last question. How long does the capacitor charge up to a voltage of 3 volts. So we're talking about voltage. It's this equation here, but what we want to find is the time t. Right. So we were given that the capacitor has charged up to a voltage of 3 volts. Okay, I'll remove the units in this case, right? So just substituting the values here, the capacitor has charged up to 3 volts is equal to the voltage of the battery is 6 volts times 1 minus e to the negative t over tau. We've calculated tau to be 0.2 seconds or 200 times 10 to the minus 3 seconds, 200 milliseconds. Because we are calculating for the time, I will use the tau in seconds, 0.2, okay. Seconds, that's the tau there. And what I want is to rearrange my equation to isolate the time t. Okay. And how do we do that, right? A little bit of revision here. So you have 6 is being multiplied to the brackets here. So before you can do anything with this exponent, in exponent of e here, you need to get rid of this multiplication sign. So you divide both sides by 6, you go 3 divided by 6 will give you 1 minus e to the negative t over 0.2. Okay, right? And before you can manipulate anything with your time t here, you still need to get rid of this 1 minus, right? Your e is being subtracted from 1, right? So you rearrange this equation. So you have e is equal to 1 minus, sorry, it's the whole thing. Yeah. Right. E to the negative t over 0.2 is equal to 1 minus 1/2, right? I simplified 3 over 6 is 1/2. Right. Just rearranging from this equation, rearranging to isolate this e to the negative t over 0.2. Okay, right. How do we get rid of this base e? Anyone remember how to get rid of this base e in order to isolate t? The ln. Oh, sorry. It's yeah. So yeah. So to get rid of this e, right? We want to get rid of this e. So if we times e on the other side, we have to times e on the other side as well. Then you have double e on both sides, and that complicates it. This e is also a base. It's like e exponent x, or it's also like 10 exponent x. And how do we get rid of bases? Yeah, logs. To get rid of a 10 base, you get the log. To get rid of e, you get the natural log or the ln. So if you take the ln of both sides, right, the e disappears. You have minus t over 0.2. It's equal to, you have to get the ln of the other side as well. Yeah, I simplified 1 minus 1/2 is just 1/2. Then it's straightforward, right? Manipulation to remove, to isolate t. So you have ln 1/2 times negative 0.2. Yes, and that will give you a time of 0.86 seconds. Good. Any question about this solution? Right. Good. right? If you're a bit rusty, just remember this. It's a formula of how to rearrange it to isolate T. The process is the same, regardless of whether you're manipulating voltage or charge or the current, right? It's Ln to get rid of that E. Good. Right, if there are no questions, then this wraps up our topic on charging and discharging capacitors and as well as direct current circuits. We'll have the workshop this afternoon, and then next week we will start our topic on magnetic fields. So I'll see you in the workshop this afternoon. Before then, keep dry and see you later.